And number 22, find a power series for f. F is equal to the second derivative with respect to x of 1 over x plus 1. That's the given series. So if we find the second derivative of this series, we'll have a function for f. How about the first derivative of this series? Using the power rule, we'll have n times x to the n minus 1. Now let's find the derivative of that. The second derivative with respect to x will be the derivative with respect to x of the first derivative, which is the derivative with respect to x of this series, which is, so since f of x is equal to the second derivative with respect to x of 1 over x, we have our final answer. A power series for f of x is that series right there. Now, it doesn't look like that's the answer that the book had, but the book is wrong. And I just checked for a value like x equals 0.25, and this series does converge to 2 over 0.25 plus 1 to the third power. So, there you go, number 22. Now let's check number 26. Find a power series for this function. Immediately, I hope you think it might be easier to find a power series for the derivative. And the derivative of the natural log of an expression is 1 over that expression, multiplied by the derivative of that expression, chain rule. So we have 1 over x squared plus 1 multiplied by 2x. And we'll rewrite x squared plus 1 as 1 in front, and the x squared being a negative x squared subtracted, because we want it to match the sum of a converging geometric series. Recall that if you start with the first term and you multiply it by the same ratio every single time, when the r value is within 1 unit of 0, that infinite series converges to the first term divided by 1 minus r. And so now this green part of the expression for f prime of x is of the exact same form as the sum of an infinite geometric series. The first term happens to be 1, and the common ratio is negative x squared. So recall that when we have a geometric series, we can write that series as the sum of the first term times r to the nth power as n goes from 0 to infinity. So we're going to rewrite what's in the brackets as a series that is equal to it, the geometric series that converges to it, because this matches the sum of that series. So our first term is 1, and we multiply it times the common ratio, which is what we're subtracting, the negative x squared, to the nth power as n goes from 0 to infinity. And so this expression is really an expanded set of terms in gray, all with the factor 2x in front. And so that 2x is really just going to get distributed to each of these terms. So we can write it inside here if we wish. Let's do that. So I just let 2x be multiplied by each term because that's what happens. I'm going to rewrite negative x squared as negative 1 times x squared, and then distribute the exponent using the properties of exponents to get this. The 2 can be either place. I'm going to write the 2 in front. And the negative 1 to the nth power, I'm going to write in the beginning, showing that it's a alternating series. And then we have x times x to the 2n, which we can rewrite as x to the 2n plus 1. All right, so now if we want a series for f of x, we just have to take the antiderivative of this series. That's dx, or in other words, that. So let's take the antiderivative, don't forget the constant, and we get that And then 2 times the constant will just be some constant. And 2 times the series is just equal to that, because there's a 2 factor on the bottom, which can divide out by the 2 factor on top. And there is our power series for f of x. Can we find the constant? Yes. If we let x equals 0, then this entire sum is 0, and we just have c equals f of 0. So what is f of 0? The natural log of 0 squared plus 1 is the natural log of 1, which is 0. So 0 equals c plus 0. C is equal to 0. And therefore, our final answer is just that series. We can find the interval of convergence by doing the ratio test here. Or, since this series was derived from this geometric series, we know that it only converges when r is less than 1 away from 0. So if negative x squared is less than 1 away from 0, then that's only true when x is between negative 1 and 1. And geometric series have interval convergences which are always open. That concludes number 22 and number 26.